Hi, in this video I'm looking at this problem here where we've got these two matrices and they are part of these matrix equations here. So for the first one I've got ax equals b, and for my second one I've got xa equals b. Now the reason that there's a difference between these two is because with the first one where we've got a times by x equals b, this is what's known as a is pre-multiplying onto my unknown matrix. Now that unknown matrix x for a lot of cases is usually considered as being x and y, but it can just be the matrix x just on its own as well. And if my matrix A is pre-multiplying my unknown matrix x, then the solution for x means that I've got to have b be pre-multiplied by the inverse of a as well. The flip side of that is where I've got the other one where I've got x times by a equals b, so the a is after it, so it's post-multiplying. So when I go to solve for x, I'm going to post-multiply by the inverse. So of course, what I'm going to need to do is find the inverse of a. So that's my first thing, is to start looking at how do I find the inverse of a. And remember, that's 1 on the determinant of a multiplied by the adjoint matrix, which if a was a, b, c, and d, means that the leading diagonal values are swapped, so d and a swap positions, and the other diagonal become the negative value of what they already are. Oops, that's a c. So we are going to apply that to our matrix A here. So in this case, we've got A equals 1, 2, 0, and 3. And so if I want to work out the determinant of A, I've got to do the leading diagonal multiplied, so 1 times by 3, minus off the other diagonal multiplied, so 2 times by 0. So if we work this out, that means that the determinant of A is just 3. So then our inverse of A is going to be 1 on 3 multiplied by, swap our leading diagonal, so instead of 1 and 3 we're going to have 3 and 1, and make the others negative, so negative of 2 and negative of 0, which is just 0. So now I have my inverse, I can go and solve my two questions. So for part A, where I've got ax equals b, that means that I've got, if I want to write it out, 1, 2, 0, 3 times by x equals our matrix b to negative 2. So when I want to solve for x, it's going to be the inverse times b. So x is going to be my 1 on 3 times 3 negative 2, 0, 1 multiplied by my b matrix to negative 2. And so now I just do this product. I'm going to leave that 1/3 there. And so now multiply the first row on to my column. So 3 times 2 is 6. Add on negative 2 times negative 2 is 4. And then my second row onto my column, 0 times 2 is 0. Add on 1 times negative 2 is negative 2. So the solution here is that 1/3 times by 6 plus 4 is 10, and 0 plus negative 2 is negative 2. And sometimes we might just write that as x equals 10/3 and negative 2/3. So that's part A. Let's have a look at part B. So for part B, if I was going to do it, that means that I have x multiplied by a equals b. So we're going to have x equals b multiplied by a's inverse. So x is going to equal 2, negative 2, multiplied by 3, negative 2, 0, 1, and we'll just chuck that 1/3 out the front. And so now if I go and try to do this multiply, I've got to multiply this row onto this column, and it doesn't work. So that means that for part B, x does not exist because I can't multiply that. If I think about my test, it's a 2x1 matrix multiplying onto a 2x2 matrix, and these two numbers don't match. So therefore, there's no solution to part B. So there we go. If we are to multiply two matrices, then if A is pre-multiplying the unknown, so it's in front, then we have to pre-multiply B with our inverse. If A is post-multiplying, in other words, it's after the unknown, then we have to post-multiply the inverse. So we calculate our inverse and try and do our calculations, but a solution does not always exist. Just because, say, A was invertible, doesn't mean that the solution to the equation exists.